Good morning, everyone. How many of us okay, just one more minute and then we'll start. Anyone has any questions? All right. Good morning, everyone. Happy Monday. So last time we were working on chapter 4. We started chapter 4 last week. And we are going to finish chapter 4 most probably by Friday. If not by Friday, then definitely by Monday. Or I can say that we will be able to finish by Friday, but we will do some practice problems on Monday. And then we have 2 review sessions next week, Wednesday and Friday. And then your test 2 will be on the following Monday, I think. Well, it's 22nd. Let me just quickly check. Yep, 22nd. So chapter 4, if you notice on Launchpad, the dates, I extended the homework, chapter 4 homework and quiz due dates, and change the due dates in your Canvas page also. So if you have any questions, let me know, depending upon when we will finish the chapter. So I extended the due dates already, but if further extension needed, we will do that. So let's talk about what we did in the previous class. We talk about probability, what is probability, rules for the probability model. We also talk about what kind of probability models we have, what are the things we need to probability. So quick review, we talk about the probability, the definition, probability. So probability is the proportion of time the outcome would occur in very long series of repetition. Again, when we discuss probability, we are talking about long-term phenomena. Then we talk about probability model. It consists of a sample space, an event, and sample space is the set of all possible outcomes. An event is a set of event, you can say a subset of sample space, a small set or a set that is coming from the sample space. We talk about random variables, but we did not discuss anything about this. So we will complete this 4.3, and your first homework is from 4.1 to 4.3. I was looking at your homework and I saw that some of you have already worked on 4.1 to 4.3 homework and started 4.4, 4.5. Again, we will be able to finish at least this so today, so that you will be able to do your first homework, which is I think due on 11th. But make sure that you start ahead of time because there are 3 attempts. So do not wait until last minute. And we kind of covered this part also, general probability rules. But again, we need to discuss few more rules depending upon what kind of events we are working with. So we discussed this probability model. We talk about the definitions of both sample space. Wait a second. Yeah. Sample space, probability rules. We also discuss about finite outcomes, or we said that when we are talking about probability model, we talk about 2 probability model. One is discrete and the other one is continuous. So where you get the finite outcomes, that means you can count how many outcomes are there. We talk about discrete or finite probability models. where you cannot count or you get infinitely many sets of outcomes, we talk about continuous probability model. How do we assign probability for equally likely outcomes? We were talking about this part in the last class. So, the last topic we were talking about independence and how to apply the rules. All these definitions we discuss. So, please go over that and let me know if you have any questions. So let's quickly talk about this example. We did not get to work on this example last time. So let's quickly work on this. It says that give a probability model for the chance process of rolling two fair six-sided dice. And you have a very similar question in your homework assignment also, where it's saying that 4x4 dice. Here we are talking about 6x6, one that's red and one that's green. So we have two dice, one is red color, one is green color, and there are six-sided. So we have six-sided. So the outcome, if we roll the first one, the outcome we get 1 to 6, and which is, let's say, red one. And when we roll the green one individually, we get the same 1 to 6. Now, when we are rolling it together, how many outcomes or how many possible outcomes are there? So when we are rolling two dice together, one is green color, one is red color, individually we know that they get outcome 1 to 6, 1 to 6 in both. But when we roll them together, what outcomes we get? So let's work. And the question is asking, what is the sample space? When we are talking about sample space, we need to tell how many possible outcomes are there. So when I roll a red die individually, I know that these are the possibilities that I get. And same thing when I roll green, these are the possibility I get. Now when we roll it together, so let's say my first one is red and the second one is green. So when I'm rolling, let's say if I get one on the red and then one on the green, then two on the green, 3, 4, 5, 6. So I'm taking the first one as red and second one as green. So the possible outcome of one being red and the other being green is we have 6 outcomes. Right? So if my red is 1, what are the possible outcomes I can get on green? Green can be 1, 2, 3, 4, 5, 6. Same thing when my red is 2, I get the same outcomes. Same order actually, not same outcomes. And same thing, same order I'll follow for 3, 4, 5, and 6. Let me put it in a nice way. Okay, so this is my sample space when I rolled 2 dice together. So how many possible outcomes are here? Anyone? How many outcomes you see here?
Is it 36?
36. And how? See, in the first row, if we look, we have 6 outcomes. And how many columns we have? 6. So 6 times 6, we have 36 outcomes. Or if you want, you can calculate 1, 2, 3, 4, 5, 6, and keep on doing. Every row you have 6 outcomes. So total 36 outcomes. Now, if my event is both 1, 1, what is the probability of getting 1 on the red, 1 on the green?
1 out of 36.
1 out of 36. Wonderful. Because this outcome is occurring only one time. Out of how many? Out of 36 outcomes. Similarly, if I'm looking for the probability of 6, 4, this is also 1 out of 36. 5, 6, 1 out of 36. So each outcome is occurring one time out of 36. So when I'm looking for the probability of equally likely outcome, each outcome is 1 out of, depending upon how many outcomes are possible. So there are 36 outcomes. So my sample space, this is my sample space, a big sample space consisting of 36 outcomes. And I can create as many possible events within this sample space, and I can find the probability of each outcome. So this probability model is your discrete probability model, because we know how many possible outcomes are there, and we can apply the thing, or we can find the probability of each particular outcome from this sample space. Now we can use the same question and change it a little bit. So instead of asking what is the probability of 1 1 or what is the probability of 2 1, we can ask it in a different way. And let me write it here because it's not in your slides. So let's say, how can you ask this question? Roll 2 dice, and here we are saying red and green. And record the total number of dots on the up faces. So I'm using the same, rolling 2 dice and getting the set of all possible outcome, which is 36. Now, instead of asking what is the probability of 1 1 or 4 1 or 5 6, where the question is, when you're rolling 2 dice, record the total number of dots. So when you're looking for the total number of dots, how do you make the sample space? When you are making the sample space, earlier you look at what comes first, what comes second. Now the question is asking, record the total number of dots. So what will be the sum or the minimum sum when you roll 2 dice? So this is the minimum, right? So 1
2.
and 1 on green, perfect. 2. So your first will be 2. So, and then next is 3, 4. You can do 3, 4, 5, 6, 7, and you keep on doing the max. You can have 12. Right? So now this was my sample space before, and this is my new sample space, depending upon how my question or what my question is asking. In the first part, it's asking you roll 2 dice and look at there, what do they have on up faces, what, and then make the sample space. And the second question, or the second part, is asking, now roll the 2 dice the same way you did here, but instead of writing each outcome, write the total number of dots on the up faces. So total number of dots, minimum we can have 2, because each die has 1 1 at least, and maximum they can have 12, because the max 6 plus 6 is 12. So now this is my new sample space. So here, when in the previous one, when we look at the probability of 1 1, it's 1 out of 36. Then we say 1 2, 1 out of 36, and each outcome is 1 out of 36. Will that be the same case here? Can I say 2 is 1 out of 36, 3 is 1 out of 36? And when I add everything, my second probability rule, it adds up to 1 whole? And the answer is no. Because now we are talking about how many outcomes? 2, 3, 4, 5, 8, 9, 10. So we do not have 36 outcomes now. How many outcomes we have?
11.
We have 11 outcomes. So when we are talking about 11 outcomes, I cannot say 1 out of 36, because the total outcomes I have 11. And in this case, when I'm assigning the probability, I cannot assign probability 1 out of 11 to each of them, because this is not the case. Now we need to find how much is the probability for 2, how much is for 3, how much is for 4. So here we need to do some work. So it's not always 1 out of your number of outcomes, number of possible outcomes. So we are using the same sample space, but the question is asking you something else. The question is roll 2 dice and look at their total number of up faces. So when you look at total number, I do not have 36 possible outcomes here. Now I'm looking at the sum of those. Though your sample space, or you are rolling it 36 times, or not 36 times, you can say that you have 36 possible outcomes. But again, my question is not asking how many possible. The question is asking what is the sum of 2 dice. When you look at the sum of 2 dice, the sample space that you make, that has 11 outcomes. Now, when you have 11 outcomes out of 36, all of them have different probabilities. They will not have equally likely probability. And let's go back to the same here. And let me so when we are looking at this, when we are looking for 1 over 1, or you can say 2. So I can get 2 only at this. This is the only possible outcome that will give me a sum of 2, right? So how many times this is occurring? 1 out of 36, right? What about 3? How many times will I get a sum of 3? So you get 3 from here.
2.
Perfect. Or you can look at diagonal. So the probability of getting a 3 is 2 out of 36. What about 4?
3.
3. And if you look diagonal, you can see that the sum of 3 plus 1, 2 plus 2, 3. And this is 3 out of 36. And similarly, when you keep on going, you will keep on checking how many, or how many times that particular outcome is occurring. That is giving me a sum of 4, sum of 5, sum of 6. And when you keep on moving, it's not all the time increasing. It will increase at certain point and then it will stop. So the max you can have is 7 on this side, right? So 7, you will get it here. So when you are looking for the probability of 7, it's 6 out of 36. And then after that, it will keep on going down. Then again, 5, 4, 3, 2, 1. Because the probability of this is 1 out of 36. So 1, 2, 3, 4, 5, it will go up till 6, or it will go up till number 7, and then it will start reducing. So when you look at the probability of this one, how do we make the table? So let's make the table. 2, 3, 4, 5, 6. So these are the possible outcomes that you have. And these are the probabilities. And we found out that the probability of this is 1 out of 36. This is 2 out of 36. And then it will keep on going down, 5 out of 36. And then you can check it from your outputs when you roll 2 dice, and then you can look at the possible outcomes. You can also look at this one from the example that is provided in your slides. Again, this is occurring only 1 time, so 1 out of 36. This is also occurring 1 time, and then if you keep on looking at diagonals, you can find 2 out of 36, 3 out of 36, and then you can make that table. So the whole point of explaining is this: sample space will change depending upon what question is asking you. Here it is asking you to roll 2 dice, and one is green, one is red, and then you can tell what are the possible outcomes. The second one, it's asking you the sum of those outcomes, or the sum of the dots on the up faces of each die. And again, we are using the same, we are rolling 2 dice, but depending upon what your question is asking, you work on that way. This has 36 outcomes. The other one, the next question, also you have 36 outcomes. But now here the probability of each outcome is 136, 1 over 36. That is not the case in the second one. For some, the probability is 136. For some, it's 236, 536, 636, and it will keep on changing depending upon what is your total sum. So the same result or the same sample space we used, and then we look at the probability of each outcome when we are looking at the sum of those two dice. Questions? So this was left in the last class. So I just want to make sure that you understand that part. Probability rules. So we talked about 4 probability rules last time. So let me just go over from there. So first rule is that the probability of an event is a number between 0 and 1. So it is either 0 or 1. When we are saying 0, so that event is never occurring or that event is not happening because its chance is 0. And when the chances are 1, that means it is occurring for sure. And in fact, this is the event that is happening again and again in every trial because the max we can have 1. So in short, we can say the probability of an event is, if it's not 0 and 1, then it's either a fraction or a decimal. And since it's between 0 and 1, it's always positive. So that is our first rule. Probability or the chance of an event is always positive. It is either a decimal or a fraction. And if not, then it's either 0 or 1. So it cannot exceed 1. It cannot go beyond below 0. So it cannot be negative and not more than 1. Second, we said that probability of sum of all the outcomes is 1. And as we looked at the rolling the die example, we have 36 outcomes, and each outcome has a probability of 1 out of 36. So when you add all of them, the sum is 36 over 36, which will give you 1. And in this example also that we make here, if you add all these, this should add up to 1 whole. So if you add 1 plus 2 plus 3 plus 4 plus 5, all numerator, it will be 36. 36 divided by 36 is 1. So no matter if it's 1 over 36 or 2, 3, 4, when you add all the outcome probabilities, it should add up to 1 whole. And that is your second rule, that the probability of the sample space is 1 whole. So when you add all the outcomes, it will not be less than 1 or more than 1. It will always be 1. So these are the first two important rules that we look if a probability model is the right model to work with or not. Once these 2 rules are satisfied, then we can see what we actually are looking for, what my question is asking, what kind of events I'm working with. Am I looking for the complement of an event, or am I looking for the disjoint events or independent events? What I'm doing it, first I need to work with these 2. Once these 2 satisfied, move to the next one. So we talk about probability of A happens is 1 minus A does not happen. And we denote this as either A complement or A prime or A power, A bar. So these are all, that means something that is not A or everything except A. And we talk about the Venn diagram. If this is my A complement is everything other than this A. And this is my sample space. So if I need to find A complement, I can subtract A from there. And if I need to find A, then I can subtract the complement. Probability of event and its complement is the total sample space, and that is 1. So probability of A plus A complement is always 1 over the probability of the sample space. So we were talking about this last time, general addition rule, and how this rule keep on changing depending upon what kind of events we are working with. We talk about union and we talk about intersection. We use or for union, either in A or in B, any, at least one. And when we're talking about this, we said and. So it should be A and B. So it should be in both A and B. So when we are talking about or, we are talking about either in A or B. So at least one should have it. When we are talking about and or intersection, that means both should have it. And we did Venn diagram, and we talk about if we are talking about this part, A and B, then this means both A and B have this part common, And this is called our intersection of A and B. So intersection is the common part. When we are talking about A union B, so we are saying both in A and B. So both A or B, so either in A or in B, and this is AND part. Since this AND part is added twice, when we write the general addition rule, A union B is their individual probabilities, and subtract the common part one time because we added it twice. When we talk about probability of A, we took this part. And then when we talk about probability of B, then also we took this part. So we took this intersection part one time out. This rule also, when we talk about this rule, and we are talking about disjoint events, so the events that are not connected or they have nothing in common, we call them disjoint events. So when we are talking about disjoint event, they have no outcome in common. There is nothing common, so their intersection is 0. Since they have nothing in common, so general addition rule, which is A union B, is individual probabilities minus their intersection. And since the intersection is 0, this part will become 0. So this will be probability of individual events sum. And when the events are disjoint or they have nothing in common. And I talk about this, I think I mentioned last time, disjoint events are also called as non-overlapping events as well as mutually exclusive events. So last time, the last topic that we were covering was independent events. And again, we talked about the word independent before in our earlier chapter. We talk about independent variable. We say that explanatory variable is independent because it does not depend on your response variable. Same thing when we are saying independent event. Two events are said to be independent if knowing the chance of one, knowing the chances of one will not affect the chances of happening of your other. Second event occur. So if you know one event that is already happened, and then you are looking for the second event, so knowing the chance or the probability of one is not going to change the chances of your second event. And the easy example is you toss a coin, you get a head or a tail. When we toss a coin, we get either a head or a tail. So I know that I got a head in my first trial, and I toss a coin again. Is knowing that the head is in the first trial going to change my chances of getting a second head or a tail? And the answer is no. Even though I know that I got head or tail in my first trial, but it's not going to affect my chances of second event happening. So the probability of this is not going to change because I know that I get head in my first trial. So these events are called your independent events. They are not dependent on each other. And when we talk about independent event, the intersection of independent event is their product of those events. So probability of A intersection B is probability of A and B. So if I'm looking for probability of two heads, it is the probability of first head times the probability of second head. So probability of H intersection H is half times half, which is 1/4. So independent events, when we are talking about two events that are independent, that means they are not dependent on each other. They are not changing the probabilities of each other. So when we are looking for their intersection is the product of those probabilities. And make sure that you have that on your sheet or a paper because there are questions in your homework assignment where they're talking about independent events also. So when two events are independent, The intersection is this. And we learned when the two events are disjoint, their intersection was 0. So how this will affect your general addition rule? So our general addition rule was probability of A plus probability of B. Let me just do it that first. Probability of A union B, or A or B, is their individual probabilities minus their intersection. So this is a general addition rule that we will apply wherever we are using A union B. But this part keep on changing depending upon what we are working with. When we work with disjoint events, this part was 0. And now we are working with independent events, so this part is the product. So you can say addition rule for independent event is probabilities, or you can say sum of their individual probabilities minus the product of these two. So it is their individual probabilities times the product of these two. So if you know the probability of A, you know the probability of B, you can find their product also. And then you can subtract it to get A union B. Questions? So this is when we are talking about independent events. So general addition rule, when we have overlapping event, when we have non-overlapping events, it is just their individual sum. So this is general addition rule, this is for independent events, and this is for disjoint events. For general addition rule, you can say overlapping events when they have something in common. Let me go back to the slide. Any questions? Okay, so let's see what's left in 4.3. So we talk about the rules. So when you need to look for if it is the right probability model to work with, add all the probabilities. If it adds up to 1, your first rule satisfied. And all of them should be between 0 and 1. And again, it should not be negative. It should not be over 1. We did this example. We talk about Venn diagram, two disjoint events. They have nothing in common. And they have this common part. So this common part is called your intersection. Assigning probability to finite. Again, we know how many outcomes are there. So we can divide with the total outcomes to get the individual probability. Is finite sample spaces called finite. If you can count how many outcomes are there, you're talking about finite probability model. And again, and this is what we have been doing. A random phenomena has k outcomes, like how we did 36 for the die one, all equally likely. Then each individual outcome has a probability of 1 over k. We divided with 1 over k. And then when the question asks us what is the probability of getting a sum of 2 or sum of 3, then we just keep on adding how many times that outcome is occurring. Independence and multiplication rule, we just talk about it. Two events A and B do not influence each other, and if the knowledge of one does not change the probability of other, those two events are called independent events. And this rule is also called the multiplication rule for independent event that we just use since it's A and B. So that is A intersection B is the product of those two events. So when we are talking about independent events, finding the A union B is easy because you know the individual probabilities of A and B, and you know their multiplication also. So let's quickly do an example with some numbers. Multiplication rules. Let's say probability of A is 0.4, and I'm just taking some number. Probability of B is 0.5, and the question is asking you, what is the probability of A union B when we know that A and B are independent events? So probability of A is 0.4, B is 0.5, and the question is asking what is the probability of A union B when knowing that A and B are independent events. Do you guys want to try it? And tell me, what is the probability of A union B? And you have very similar questions in your homework and quiz also.
Is it 0.20?
0.20. So I'm asking probability of A union B. I think you're solving for A intersection B.
Okay.
We're on the right track. So how he said 0.20 is like probability of A is 0.4 and probability of B is 0.5, right?
Would it be 0.7?
0.7, yes. So you guys are on the right track. So A union B is probability of A plus B minus the intersection. And your intersection will come from here, and you know their individual probabilities. So they're individual 0.4 plus 0.5, and what you get here, plug it here, and then you get the union. So finding the probability of A union B is not hard. The only part is you need to know what kind of events you are working with. If you are working with disjoint event, then it's not 0.7, then it will be 0.9, because for disjoint event, this is 0. And if they are overlapping events, then we know that we should know their probability. If their probability is 0.3, then you can subtract that part. Again, it depends upon what the question is asking you. Questions?
Yeah. Can you just explain why it's 0.7? If the A, not the A union, but the one on the top, if that would be A times B, that would be
This one?
Yeah. So that would be 0.20. So that would be 0.9 minus 0.20, right?
Yes. So same formula, that probability of A union B, it's their individual probabilities. General addition rule minus the intersection.
Oh, I'm sorry. I got it.
Okay, that's fine. Maybe somebody else need the explanation. So let me just go over since we are here. So probability of A is given to us and B is given to us. The only part is we need to find this. And if we know what kind of events, if it's disjoint event, this will be 0. And that you add this, that will be your answer. But if it's not disjoint event, what other event we are working with? So currently we are using independent event. And the question also says that A and B are independent. That means knowing the chance of A is not going to change anything for your probability of B. So first thing, find that part. And finding that part is you multiply these two and then plug that value here and then solve. And you get the union. So again, that's why I said that this general addition rule is important. Once you know the rule, then you need to just see what kind of events you are working with. And then accordingly, you can just look how your intersection or what will be the value of intersection. If they are overlapping events, the intersection is given to you. If they are disjoint events, we know that the intersection is 0. If they are independent events, if we know A and B, then we can find their intersection by multiplying. So this is about independent events. Anyone has any other questions? So I'm assuming that this part is making sense. Applying the rules, again, we have been working on how to use the formula and where to apply. So let me just talk about 4.3 because your first homework is including 4.3. Random variables we also talk about discrete, and we have been using the example of discrete random variable where we know how many outcomes are there. And in previous chapter, in first chapter, we talk about continuous random variable. We talk where we use uniform distribution and we look at the area under a specific range. Let's say if we are looking at the area under this range, and if we are looking for this range, that means I do not know how many outcomes are there. There are infinitely many sets of outcomes, so I cannot assign individual probability. So probability of x equal 2 is 0. Probability of x equal 5 is 0. Or any whole number you are looking for, 3, 4, 5, it's 0. But I can find the probability in this range using normal distribution, where we can find the area under the curve either using the table or using the calculator. That is your continuous random variable. And again, normal distribution. So let's just quickly do 1 or 2 examples so that it will refresh your chapter 1 content. So same one. It says that a probability model describes the possible outcomes of a chance process and the likelihood that these outcomes will occur. A numerical variable that describes the outcome of a chance process is called your random variable. And random variable takes numerical values that describes the outcome of some chance process. So this example, let me explain it on the side what they have it here. So you toss a coin, and what outcomes we get? We toss a coin, we get either a head or a tail, right? That's my first possible outcome. So let me toss a coin again, and when I toss a coin again, I get a head or a tail, head or a tail. And the chance is this, because they are all independent events. Now, the question is asking, write the sample space. If I'm writing the sample space, that means I'm looking for all possible outcomes. One outcome is this, head and head. One outcome is this, head and tail. One outcome is this. So I can see how many possible outcomes are 4. What is the possibility or what is the probability of getting 2 heads? 1 out of 4, 1 out of 4. So this is a discrete probability model because I know how many outcomes are there and what is the probability of each outcome. And this question can be asked in that way also, like how your example has. Now consider tossing a fair coin 3 times. So instead of 2, we toss it one more time. Head, tail, head, tail, head, tail, head, tail. So how many possible outcomes we get? 1, 2, and then similarly you can say that 2, 2, 2, 2. So you will get 8 possible outcomes, right? So you can write your sample space again, saying that S is head, 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 tail, and you can keep on doing until you get all these 8 outcomes. Now the question is asking you, very similar what we did for rolling 2 dice and looking at their sum. Similarly, here is saying let X is the number of heads obtained. If X is the number of heads in rolling or tossing a coin 3 times, the maximum, how many maximum heads we can get? 3, right? Because we are tossing a coin 3 times, so we can get 3 heads, but we cannot get more than that. So similarly, like how you make an outcome, so your possible outcomes are either you get 3 tails or head, tail, tail. There's this 1 head, 2 head, and 3 head. Now, if the question is asking the same question that we said that we roll a die, we roll 2 dice and we look at the possible outcomes, we have 36. Same thing here, we are saying we toss a coin 3 times and look at their possible outcomes. So we have 8 outcomes. If you count 1, 2, 3, 4, 5, 6, 7, 8. But now the question is saying X is the number of heads obtained. The number of heads maximum you can have 3. And when you get all 3 tails, the number of head is 0. When the number of head is 0, what is the probability? 1 out of 8. Because you have 8 outcomes. When your X is 1, that means you can get 1 head. Either way. Does not matter that head is in the middle or in the side or in the front or in the back. So number of heads, only 1 head, 3. 2 heads, 3. And 3 head is 1, 8. And again, if you want to see if this is the right probability model to work with, each of these outcomes are between 0 and 1. And when you add everything, it will add up to 8 over 8 divided by 1. 8 over 8 equals 1. So same thing like how we did the rolling die example or tossing a coin. The question, again, sample space finite when you get the possible outcomes. But when you are making or when you're explaining that discrete sample space and looking at the probabilities of each outcome, it depends what the question is asking you. Is the question asking you for each outcome? Or is it asking you the number of heads or number of tails or head in the middle, or head in the right side, or head in the left side, again, you will look at the probabilities differently then. But those two probability rules will still remain the same, that is between 0 and 1, and the sum adds up to be 1 whole. So discrete probability model, when we talk about discrete probability model, we can find the probabilities of each outcome depending upon what we are looking for. And then we can find the mean or the expected value of that discrete outcome. And how to do that? So there are two types of random variable, discrete and continuous. We can find a way to list all possible outcomes of a random variable and assigning probability to each one. Then we call it as discrete random. So again, discrete means finite. Discrete random variable takes a fixed set of possible values with gaps between, and the probability distribution of discrete random variable xi and the probability pi. So this is your first, second, third, and respected probabilities. So each outcome and its probability, and when you add these probability, the sum should add up to be 1 whole, and each probability is between 0 and 1. That we just did in this example here. So this is their x, and this is their probability. Value is your x, and probability is your pi. This is your pi for 0. This is pi for 1, 2, and 3. So each probability, pi is the number between 0 and 1, and the sum adds to be 1 whole. To find the probability of an event, add the probabilities of the particular value that makes up the event. If you are looking for the probability of particular event happening, what do? We look at their corresponding probabilities and add. So let's look at this example. A liberal art college posts the grade distribution for the course. In recent semesters, students in one section of English received this: A's, B's, C's, and D's, and F's. Here is the distribution of the discrete random variable called grade points, where A is 4, B is 3, C is 2, and so on. And this value is given. And the question is asking, what is the probability that a randomly student got a B or better? When we are saying B or better, B is at 3. So this is my B. And if I'm saying B or better, the better is B and A, right? So if you are looking for the probability of B or better, so you are going in this direction. So you are looking for greater than equal to 3. So greater than equal to 3 means 3 and the higher number to 3, which is 4. So you add these two and you can tell the probability of a randomly selected student get a B or higher is 74%. So when it's in decimal, you multiply it with 100 to get the percentage, and you can say that it is 74%. Questions? All right, continuous random variable. And again, we have done continuous random variable in chapter 1, but we did not mention there in terms of probability. So let's quickly talk about that. Discrete random variable commonly arises situation when it involves counting something. And again, when you are counting something, you know how much. But when you are measuring something, you do not know how much is the total outcome, then we call it as continuous random variable. So again, when you are counting something, you work with discrete random variable. When you measure something, you work with continuous random variable. A continuous random variable y takes on all values in the interval of numbers. Again, what interval we are looking for: less than, greater, in between. And we have done that in chapter 1, where we look at the left-sided area, right-sided area, and in-between area. The probability distribution of y is described by a density curve. The probability of any event in the area under the density curve and above the values of y, that makes up the event. And again, when you look at the example, then it will make more sense. So when, as I said, that probability at each particular outcome in continuous interval is 0. If you're looking at any number, then it is always 0. X equals 4. So we cannot find the probability at one particular outcome because there are infinitely many sets of outcomes and we cannot divide with. We know how many times 2 is occurring, but we cannot divide with infinity. So probability at each particular outcome in continuous probability model is 0. While that is not case in the discrete, because discrete, you know how many possible outcomes are there, and then you divide with that. So continuous probability y has infinitely many possible values. So in continuous model, assigning probability 0 to individual outcome. And make sure you remember that part because you will be tested on that either in homework, quiz, or test. So when we are looking at the probability of each outcome, we can find that in discrete because we know how many outcomes are there. But in continuous, we do not know how many outcomes are there, so we cannot find that. And this is what we have done before. So I just look at the time, it's 11:51. So I'll stop it here. And I think you guys are good to do your homework assignment. First one, we have done these uniform, normal and uniform both in chapter 1. So take a look at that. I will go over these examples in Wednesday's class as well. But I think you're good to do your first homework. Thank you, everyone. And I'll see you guys on Wednesday. Enjoy the sun.
Thank you.
You're welcome.